Before we discuss decoding of linear block codes, let us solve some problems today. So, first question that we are going to look at is, consider a linear block code C whose parity check matrix is given by this, and you are asked what are the code parameters n and k, n which is the block length, code word length, and k is the size of, is the dimension of the basically information sequence length is k. Now, how do we solve it? We know, we will first find out what is the rank of this matrix H. Now, you can see this is a 4 cross 7 matrix, right. So, the maximum rank possible is 4. Let us see whether it has rank 4. Now, if you add row 1, 2 and 3, what do you get? 1, 1, 1, 1, 0, 1, 0, sorry, 1, 1, 1, 0, this is 0, 0, 1, 0. This is what you get. You can see this is 1, this is 1, this is 1, this is 0, this is 0, this is 1, and this is 0. And what is row number 4? This is exactly same as this. So, you can see row 1, row 2, row 3 and row 4 add up to 0. That means, it does not have rank 4. So, maximum rank possible is 3. So, let us see if any 3 rows combination add up to 0. So, let us see if we consider some of these 2 rows. This is what? 1, 1, 0, 0, 1, 0, 1. Now, none of the rows are equal to this, you can see. If we consider this row and this row, we add these 2 rows, let us see, what do we get is 1, 0, 1, 1, 1, 0, 0. Now, note none of these rows R2 and R4 is equal to this. So, these set of 3 rows basically they are independent. Let us try adding up this and this. So, if we add first row and 4th row, what do we get? 0, 1, 1, 1, 0, 0 and 1. Now, note row number 3 and 2 are not same as this. So, like that we can check for example, row 2 and 4, we add up row 2 and 4, what do we get? 1, 0, 1, 1, 1, 0, 0. Now, note row number 3 and row number 1 are not same as this. So, we can see that any 3 rows do not add up to 0. So, the rank of this matrix H is 3. So, if the rank of this matrix is 3, now we know parity check matrix is n minus k cross n. So, n minus k is in our case equal to 3, and what is n? N is number of columns of this. So, that is 1, 2, 3, 4, 5, 6, 7. So, n is 7. So, that would then give us k equal to 4. So, this is an example parity check matrix for a 7, 4 linear block code. Okay. Now, let us look at another problem. You are given a set of code words, and what are these code words? These are binary code words. So, this is all 0, 1 1 0 0 1 1, 0 1 1 1 0 1 and 1 1 all 1 sequence. And the question that has been asked is this a linear code? Is this a linear code? Now, what do we know about linear code? A linear code should have all 0 code word, which this code word has, and sum of any 2 code words is also a valid code word. So, let us see. So, let us see if sum of all code words is already a valid code word. So, let us call this V0, V1, V2 and V3. So, what we want is all possible combinations of V0, V1, V2, V3 should also be a valid code word. They should be in C. So, let us see. So, as I said, we take V0 to be all 0 code word, V1 is given by this is V1, this is V2 and this is V3. Now, let us see all possible combinations of V1, V2, V3, the non-zero code words. So, we consider V1 plus V2. What is V1 plus V2? So, V1 plus V2 is, you can see this is 1, 0, 1, 1, 1, 0. This is given by this. Now, is this code word in C? We do not see any code word which is 101110 listed here. That means this C is not a linear code. Why it is not a linear code? Because sum of any 2 code words is also a valid code word. Now, V1 and V2 are valid code words in C. So, sum of V1 plus V2 should also be in C, but we notice that 101110, which is sum of V1 plus V2, is not there in C, and that is why we said that C is not a linear block code. Now, my next question is, can we add additional code words here such that C becomes a linear block code? Now, how do we do that? To do that, we will have to ensure all possible combinations of these code words is also there in C. So, let us then compute V1 plus V3, which is basically given by 001100. Let us look at V2 plus V3, which is given by 10010, and let us look at V1 plus V2 plus V3 is basically given by 010001. So, note that I have listed all possible combinations of these code words here. Now, none of these sums are there in this linear block code. So, if we add them in this set of C, set of code words, then our block code C will become a linear block code. So, if we want to make it a linear block code, what do we need to do? In this set of 4 code words V0, V1, V2 and V3, we need to add these set of code words, which was basically V1 plus V2, this is V1 plus V2, this is V1 plus V3, V1 plus V3, then this one is V2 plus V3, V2 plus V3, and this one was V1 plus V2 plus V3. So, let us look at these 2 code words. This is V1 plus V2 and this is V1 plus V2 plus V3. So, if we add these 2, what we will get is V3. We can double check. So, if we consider add these 2, the first bit will be 1, this 0 plus 1 will be 1, then 1 plus 0 will be 1, then 1 plus 0 will be 1, then 1 plus 0 will be 1 and 0 plus 1 will be 1, and this is already there in this set of code words. This is V3. Okay. Similarly, take this 2. This one is V1 plus V2 and this is V2 plus V3. If we add them, what we get is V1 plus V3, we will get this. If we consider these 2, we will get V2. If we consider this, we will get V3. If we consider these two, sum of these two, we will get V3. If we consider sum of these three, what we will get? We will get V3. So, you can see basically linear combinations of all these code words is already there in this C. So, this C which contains this set of 8 code words is a linear code. And what are the parameters n and k? Now, the length of the code words is 6. Each of these code words are 6 bits. So, that is why n is 6, and there are total 2k code words, and in our case 2k is basically 8. So, k is 3. So, this is basically a 6-3 linear binary code. Now, if I ask you, tell me what is the generator matrix that will generate this set of code words. Now, how can you do that? So, we know the generator matrix is basically a k cross n matrix, right. So, if you take basically 3, k in this case is 3, if you take 3 code words which are linearly independent, basically if you take them and form them as rows of your generator matrix, then you get your generator matrix. So, I just took this V1, V2 and V3, and you can verify that rank of this matrix G is 3, it is full rank. Okay. So, then this G will be able to, this generator matrix will be able to generate this set of code words. Now, can we put this, is this generator matrix in systematic form? The answer is no, because if to get it in systematic form, what we need is our generator matrix should be of the form like this or something like this. Okay. But this is not in this particular form. So, we will have to get some identity matrix and some matrix P. Now, by doing elementary row operation, we can put this in systematic form. So, let us do that. So, note, if we want to get, let us say this in the form of identity, what do we need? We would need basically here we would need a 0, here we would need a 0, here we would need a 0, here we need a 0, right. So, let us first try to get this 1 to 0. Now, how can we make this 0? So, if we do this transformation, that row 3 is row 3 plus row 1. So, row 3 is row 3 plus row 1. If we do that, then 1 plus 1 this will be 0, 1 plus 1 this is 0, 0 plus 1 this is 1, 0 plus 1 this is 1, 1 plus 1 this is 0, and 1 plus 1 this is 0. Okay. So, we got a 0 here, right. Next, we want a 0 here, we want this, we want to make this 0. So, how can we do that? We do this transformation that row 2 is row 3 plus row 1, row 2. So, if we row 2 is row 2 plus row 3, then what is going to happen? This will remain 0, this will remain 1, but this 1 will become 0. So, let us do that. So, this is 0 plus 0 is 0, 1 plus 0 is 1, 1 plus 1 is 0, 1 plus 1 is 0, 0 plus 0 is 0, and 1 plus 0 is 1. Okay. So, we got these zeros, we got this 0. Okay. Now, what do we have to do? We will have to get this here, we have to get a 0. So, how can we get a 0 here? We will do this transformation. We will add row 1 and row 2 and replace row 1 by this. So, we are going to add these 2 rows. If we add these 2 rows, what is going to happen? this 1 will remain 1, 1 plus 1 this will become 0 and this will remain 0. This will be 0, this will be 1 and this will be 0. So, if we do this transformation, what we get is this. Now, note that this is our identity matrix, it is a 3 cross 3 identity matrix, and then this is your another matrix P. Okay. So, by doing elementary row operation, we are able to get our generator matrix in a systematic form. And if we have a generator matrix in a systematic form, then we can very easily find out the parity check matrix in systematic form. So, this is like I k p, then this H matrix will be P transpose I n minus k. So, this is basically your P transpose. So, this 0 1 0, this will come here 0 1 0, 0 0 1 is this is 0 0 1 and 1 0 0 is this 1 0 0, and then you have this identity matrix which is here. Okay. Next, we are given a parity check matrix H of a linear block code with parameter n and k, and it is given that this code C has both odd weight code words and even weight code words. In other words, the number of ones in the code words, it contains both odd number of ones as well as even number of ones. And we are constructing a new code that we are calling as C1, and the parity check matrix of the new code C1 is given by this. So, how do we find this new matrix parity check matrix H1? We are adding a new column which is 0 in the initial rows, except in the last row where there is a 1, and here we have put our original n minus k cross n matrix, and the last row is basically all ones. Okay. So, the dimension of this matrix is, so number of rows is n minus k plus 1 and number of columns are n plus 1. Now, you are asked to show that the code generated by this parity check matrix H1 is a linear code with parameters n plus 1 and k. Second thing you are asked to prove is that all the code words of this new code C1 will have even weight, that means they will have even number of ones in them. The third thing that you have to prove is this new code C1 is obtained from old code C by adding an additional parity bit which we are denoting by V infinity to the left of this code word. And how do you select this parity bit V infinity? If the original code word has odd weight, then you put V infinity as 1, otherwise if the original code word has even weight, then you put this V infinity as 0. So, let us prove one by one. Let us first prove this, that code generated by this new parity check matrix is basically a new code with n given by n plus 1 and k given by k. So, as we know that this H matrix has these dimensions, because we are adding a new column and we are adding a new row. Next, now what is the rank of original matrix H? The rank of the original matrix H is n minus k. That means, the n minus k rows of the original parity check matrix H are linearly independent. Okay. Now, go back and look at the new construction. So, these n minus k rows are linearly independent, and what have we added here? We have added 0 here. So, these new rows will, this new n minus k rows will also be linearly independent. So, that is what we are saying, that since n minus k rows of the original parity check matrix H are linearly independent. So, the first n minus k rows of the original parity check matrix H1 will also be linearly independent. Now, let us look at the last row of this new parity check matrix H1. Note that we have a 1 here and these are all 1s here, whereas here all of these are zeros. So, this new row will also be linearly independent from any of the other rows of this parity check matrix H1. So, any linear combination including the last row of H1 will never result in a all 0 vector. So, what does it mean? It means that n minus k plus 1 rows of our new parity check matrix H1 are linearly independent. Hence, the dimension of H1 is n minus k plus 1. Now, how do we find the dimension of basically the null space of this parity check matrix H1? This is given by, so number of columns is n plus 1, the dimension of H1 is given by this. So, this is the dimension of the null space of this parity check matrix. So, then basically the number of information bits is then k and number of coded bits is n plus 1. So, this proves that C1 is an n plus 1 k linear code. Next we are going to show is every code word of C1 has even weight. So, how do we prove this? Please note that the last row of this parity check matrix H1 contains all 1 vector. If you go back, recall the last row of this parity check matrix has all 1s, and if V is a valid code word, what property does it satisfy? If V is a valid code word, then V H transpose should be 0. Now, let us take a code word, let us say there exists a code word with odd weight, which is generated by, described by this parity check matrix H1. Now, if we do V H transpose, so when you are going to take the inner product of this code vector V with the last row of this parity check matrix, what will you get? You will essentially get sum of, so basically if you do V H transpose, so your H is of the, so V H transpose where H is H1 transpose H1 is given like this, this is all zeros, you have your parity check matrix H and you have here all 1 vector, sorry, you have your, this is 1, this is 1 and this is all 1 vector. Now, when you do V H transpose, so let us say V is your V0 to Vn minus 1. When you do VH1 transpose, what you will get is V0 plus V1 plus V2 up to Vn minus 1 is going to be 0. Now, if this V has odd number of 1s, this sum cannot be 0, right. Hence, we prove that V has to have even number of ones, because we know if V is a valid code word, then V H1 transpose should be 0. So, if we do V H transpose, because the last row of this parity check matrix H1 is all 1, the condition that we will get is the individual components of this parity code vector V, V0 plus V1 plus V2 plus V3 up to Vn minus 1, basically Vn minus 1, they should all add up to 0. Hence, we cannot have an odd weight vector which will give VH transpose, VH1 transpose to be 0. Hence, every code word in C1 has even weight. Next, we are going to prove how we can generate this new code C1 from the original code C. And what did we mention? We mentioned that this new code C1 can be obtained from the original code C by adding an extra parity bit, which we are denoting by V infinity, to the left of the original code word V in this fashion. If V has odd weight, then V infinity is odd parity, and if V has even weight, then V infinity is 0 parity, is 0, is even parity. So, let us prove this. So, let us see, let V be a code word in C, then V H transpose will be 0. Now, we are extending this original code V by adding a bit V infinity to its left. So, we are defining a new code word of length n plus 1, which is defined as follows. So, this is your original code word V, which is basically V0 to Vn minus 1, and then this is the additional parity bit that you added to the left. Now, if V1 is a valid code word, then it should satisfy the property that V1 H1 transpose should be 0. And what is our H1? Again, please recall, our H1 is a form like this. So, the first column here is 0, then you have here the original H matrix H, and this is all one vector. So, when we do VH transpose, so when V1 will be multiplied by this last row, what we will get is condition of this form. V infinity plus V0 plus V1 plus V2 plus Vn minus 1, that is basically should be equal to 0. Okay. Now, how are we getting this condition? Again, we are making use of the fact that V1 H1 transpose is 0, and H1 is a form like this. So, when we do V1 H1 transpose, the last row which will be in H transpose will be last column. If we multiply V with that H1 transpose column, what we would get is something of this form. Now, this should be equal to 0 if V1 is a valid code word, right. So, if the sum has to be 0, what do we need? So, if the original code word is odd weight code word, we need V infinity to be 1, and if the original code word is even parity, then this new parity bit should be 0, and that is basically the proof how we can extend the original code to construct a new code. And this is basically, if this is equal to 0, we know that V1 H1 transpose is 0. So, V1 is a valid code word in C1, and total there are 2k code words. This we have already proved in the first part, that there are total 2k code words of length n plus 1. Okay. So, with this I will conclude this lecture. Thank you.